everyone, and welcome to week 11. The semester's flying by. This week we're going to discuss chapter 13 in your textbooks, which is on running water. And this week and next week, I'll be covering topics in hydrology and hydrogeology. And just to remind you, that's kind of my specialty. I work for Idaho Department of Water Resources as a hydrogeologist. So this week in office hours or in any other scheduled appointments, if you have any questions about the subject material or potential careers or internships in hydrology or hydrogeology, please let me know. This photo here is actually of a local stream called Dry Creek, which runs up near Bogus Basin, down towards the base of Bogus Basin Road, and is a common place for hydrologists from Boise State University to study running water. So I'm going to begin discussing running water in the context of Earth as a system, and then sort of narrow our focus down to smaller scales of running water. So Earth is rather unique in the solar system because it's the right size and distance from the sun to have an abundance of liquid water. I don't want to say it's the only body within our solar system that has liquid water, because we just discovered that there's liquid water on the moon. There's some evidence that there's liquid water on Mars, and there may be liquid water on some of the moons of Jupiter and Saturn, like Europa, for example. But I digress. Earth, as far as we know, is the most ideal body within the solar system to house liquid water. And the reason why there's water on the surface of the Earth is due to mantle convection. So if you remember when we reviewed plate tectonics and we reviewed the different layers of the Earth, how hotter and less dense materials from within the Earth rise towards the surface, and how colder and denser materials near Earth's surface sink towards the center of the Earth. Well, water, both in liquid form and in vapor form, is rather light compared to a lot of the other compounds within the mantle, and that causes water to make its way towards the surface. A lot of it actually makes its way towards the surface in the form of water vapor when there's volcanic activity, and then that water vapor might eventually condense into liquid form or solid form. And within the context of Earth as one entire system, the hydrologic cycle describes the movement of water through that system. So if you remember from some of the earlier lectures, we discussed the geosphere, the hydrosphere, the atmosphere, and the biosphere as sort of four different systems within the Earth system. And we also discussed how water cycles through each of those different spheres. So water is certainly something that connects all of the different spheres within the Earth system. So let's talk a little bit about the distribution of Earth's water. So this might surprise a lot of you, but 96.5% of all of the water on Earth is actually within the oceans. So anything that you see as fresh water only adds up to about 2.5% of the total water on Earth. And then you have another 1% or so that's either saline lakes, which are lakes that contain a lot of salt, or groundwater, so water that is trapped in pore spaces that we can't see on our surface. Then if we go from total global water and sort of zoom in on fresh water, you can see that amongst that 2.5% of the total global water that's fresh water, About 68.6% of that is trapped in glaciers and ice sheets. So much of that is in, Antarctica and Greenland, for example. And this is why when folks talk about global climate change and warming of the atmosphere and the oceans, there's so much concern because the vast majority of fresh water is trapped in these glaciers and ice sheets, and a ton of that ice or solid form melting into a liquid form could cause very large changes to the Earth system as a whole. Second to glaciers and ice sheets, in terms of freshwater on Earth, we have groundwater, which makes up about 30% roughly of all of the freshwater. And then lastly, we have surface water and other fresh water, only making up 1.3% of freshwater on Earth, which, if you recall, only 2.5% of all water on Earth is freshwater. So we're talking about 1.3% of 2.5%, making up the surface water that we see and most commonly think about as water within our system. So then if we were to continue to zoom into what we're most familiar with, and we look at surface water and other fresh water on Earth, or that 1.3% of total fresh water that we just talked about, most of that is snow and ice, and then followed by lakes, soil moisture, swamps, and then rivers, water and organisms, which is what biological water is, and then the atmosphere. So there's a lot of water trapped in glaciers and ice sheets and snow and ice amongst the fresh water, but the vast majority of water is salt water. So how does water move through the hydrologic cycle? How does it move between the different Earth spheres? And how does it move between different layers of the Earth? Well, you can think of the beginning of the hydrologic cycle as when water evaporates from the oceans or plants or soil or other surface water, and then moves through the atmosphere. So you have a transition from liquid phase to gaseous phase. And then water leaves the atmosphere via precipitation. So you have the gaseous phase of water that condenses to either the liquid phase or the solid phase, and then falls back towards Earth's surface. It could fall on land, it could fall over the open oceans or other bodies of water. Once precipitation hits the ground, it does basically one of three things. It can either soak into the ground, which is called infiltration. It can run over the top of the land surface, which is called runoff. And that is, you're effectively looking at runoff when you look at a stream or a river. Or it can evaporate back to the atmosphere. And that's called evaporation. If it is just the water itself. And it's also called transpiration if the water is taken up through a plant's roots and then evaporated from the stomata, or essentially the pore space within the leaves of the plant. So this slide shows a good example of what the hydrologic cycle looks like within our system. So again, if you start with evaporation from an ocean, then you have condensation of that water vapor, and we'll talk about why water changes phases from liquid to, or from gas to liquid to solid later in this lecture. And then after condensation occurs, then precipitation, in the form of rain or snow or hail, occurs, and then that precipitation is partitioned into either infiltration or runoff or evaporation / transpiration. Infiltration can lead to greater amounts of groundwater, and then groundwater moves, and so that groundwater can feed lakes and rivers, and then runoff simply brings that water that fell as precipitation ultimately back towards an ocean if it doesn't evaporate before it gets there. So now we've talked about the global hydrologic cycle and how water moves through different Earth systems. So let's zoom into like a hill slope level. So this beautiful diagram, which I once drew for a presentation related to my master's, shows all the different things that happen on a hill slope scale hydrologically. So you have precipitation falling as either snow or hail or rain, and then that precipitation either runs off across the land surface as runoff or infiltrates into the soil or evaporates and pools on the surface and evaporates, or evaporates while it's running off. Those are pretty much all the different things that can happen. Obviously with snow, if you end up with a snowpack and the snow doesn't immediately melt when it lands on the ground, then you have sort of a storage reservoir for water in the form of snow, and then you have a delayed runoff or infiltration as it sits there in the snowpack. So assuming that you have water that infiltrates into the soil, some of that water will evaporate from the soil. Usually it doesn't evaporate from more than a couple feet down within the soil. If it infiltrates deeper than that, then the only reason why it would enter back into a vapor phase before resurfacing is if a plant like a tree, for example, takes that water up into its roots and then transpires it, which transpiration again is just the evaporation of water from within the stomata or the pore spaces on the leaves of the plant. And then some of that water that infiltrated into the soil might flow through the soil towards something like a stream. Some of it might continue to infiltrate deeper into the groundwater system. And it's important to note that groundwater and stream water are often connected to one another. They're connected systems. So a lot of times, if a stream is gaining groundwater, or groundwater is seeping into a stream bed, then the stage or the height of water within the stream might represent the height of groundwater in that location, or the water table. And then in other cases, you have a net loss of stream water that then infiltrates down into the groundwater system. So the groundwater and surface water systems are very connected with one another in that way. And that's why in Idaho, we have conjunctive management of water law, which means that we take into account what's happening in the groundwater system as well as the surface water system when enacting new water laws. Some states aren't so fortunate. They have old water laws where you simply assume that groundwater is disconnected from surface water, which can lead to some pretty catastrophic things, like someone with a groundwater right pumping a bunch of groundwater right next to a stream and acting like it's not actually stealing water from that stream when they do that, which can lead to some pretty catastrophic dewatering of streams. In fact, as is seen in a state that I used to work in, New Mexico, with some of the pecan orchards down near the border. where folks downstream of New Mexico were essentially getting robbed of water, unfortunately. All right, so now I have a little bit of an in-class activity for you. It's a thought exercise, and obviously we're working remotely, but I just want you to take a minute to think about this and try and answer this yourselves before you move on to the next slide. So assuming that there's zero evapotranspiration, which means zero evaporation or transpiration, what factors determine whether precipitation or snowmelt is partitioned into runoff or infiltration? So the question that I'm asking is basically, what factors determine how precipitation or snowmelt is divided into runoff or flow along the surface, along the ground surface, versus infiltration, where it actually infiltrates down into the soil. Okay, so I hope some of you have come up with some interesting answers for this, and I would be interested to talk with any of you about your thoughts on it. My understanding is that there are basically two reasons why precipitation as rain or snowmelt would be partitioned into runoff on the ground surface. Reason number one would be if the precipitation rate or snowmelt rate exceeds the maximum infiltration rate for the soil on the ground surface. So essentially you can think of it as like precipitation falling faster than that soil can absorb that water. In which case the excess water that can't infiltrate because precipitation is happening too fast runs off across the land surface. The second reason why you might have runoff across the land surface instead of infiltration is if the pore space near the surface, near the land surface, is already full of water. If it's already at capacity and it can't fit any more water, then the excess water that falls beyond that point would simply run off across the land surface. And those are basically the two ways that you would see runoff instead of infiltration. I encourage you all to think about this, however. A lot of people think about stream flow being caused by runoff primarily, but as I just discussed with you on the last slide, surface water bodies like streams and groundwater are often connected to one another. So I guess I encourage you to think about when in your life you've actually seen runoff occurring across the land surface. Because for me, the only time I've ever seen it is when the rain or the snow melt was occurring on top of a surface that would have an extremely slow infiltration rate or be almost like impenetrable. A good example of something like that is blacktop or concrete. Another time when I've seen runoff just sort of moving across the land surface when it wasn't within a stream is, a large snowmelt event or a really fast precipitation event. But those events are rather rare and not responsible for all of the flow in a river or a stream. So this slide continues to expand upon what I was just talking about, which is if you have precipitation, are you going to see runoff or infiltration or both? So as I mentioned, the intensity and duration of rainfall definitely matters. The amount of water already in the soil. So again, if the pore space in the soil is already full of water, then that water will run off. Water already in the soil is called antecedent soil moisture. The type of geologic material. So if you have something like a sand or a gravel, then that will probably be able to have a pretty fast infiltration rate. So you can have a lot of water infiltrating through it quickly. Versus, again, if you have something like a blacktop or concrete, water's going to have a lot of trouble making its way through that, and that promotes runoff. The slope of the land surface as well. So if you have a steep slope, then it means that any water that hits the land surface might start moving downslope faster, and therefore promoting runoff versus infiltration. And then the nature of the vegetative cover, because if you have a large canopy that's sort of catching a lot of the precipitation before it reaches the ground surface, then a lot of that water might ultimately slowly drip through the canopy and then infiltrate into the soil rather than run off, because the water wouldn't be hitting the land surface fast enough to cause runoff in that case. And then, of course, plants transpiring water, taking water up through their roots and then transpiring it, has an effect on soil moisture and therefore infiltration versus runoff as well. So I sort of alluded to this already, but how exactly is runoff generated? Well, basically, precipitation pools on the land surface when the rate of precipitation exceeds the hydraulic conductivity of the geologic materials at the land surface. And the hydraulic conductivity in this case is sort of a hydrology term for how fast can water move through that particular geologic material. And again, the other way that precipitation can generate runoff is when the soil pores are already full of water and no more can infiltrate through the pores because they're already full. So a little bit more on the effect of vegetation on runoff and infiltration. I guess I already talked about this a little bit as well. Getting ahead of myself here. So canopy cover has a pretty major impact on runoff versus infiltration because the canopy can collect water and then you have throughfall through that canopy, and that alters the way that the water is making its way to the land surface and kind of slows it down and distributes it over time. And then also you have evaporation of the water that hits the canopy before it makes it to the soil surface, and transpiration, or water taken up through the roots that's transpired through the stomata and the leaves back to the atmosphere. So one interesting thought experiment here is to look at the picture in the upper right of this slide and the picture in the lower left of this slide and think about the differences between the type of runoff that you would see in those two different types of environments. In the upper right, you have a much more robust canopy, and in the lower left, you have a ground surface with a much lower hydraulic conductivity, or a much lesser ability to transmit water because it's largely pavement and concrete. So the photo in the lower left, that sort of landscape would lead to a lot more runoff, versus the landscape in the upper right would lead to a lot more infiltration as a percentage of the water that fell as precipitation. All right, so we've talked about why precipitation would become runoff rather than infiltration or evaporation. But let's talk about how runoff forms into streams and rivers. So it typically starts as sheet flow. So you can think of this as kind of how it sounds, which is a sheet of water flowing over the land surface. And then it will develop into tiny channels called rills. So if you're ever looking at a hill slope, for example, and you see that there's been erosion into little lines and it looks like sediment has been moved, then that's probably where sheet flow developed into tiny channels called rills and basically concentrated into one area. And then rills meet with one another to form gullies. So a gully would be if you're hiking in the foothills and you have to walk down in elevation significantly and then walk up in elevation significantly on the other side. You may not see water flowing through the gully, but that doesn't mean that it's not flowing through the gully after precipitation or snowmelt events that generated sheet flow and rills and filled the gullies with water. And then ultimately gullies join to form brooks, creeks, or streams. So the definition of a stream is any water that flows in a channel regardless of size, and a river carries a substantial amount of water and has many tributaries. So a river is essentially larger than a stream, and a stream is larger than a gully, even if there's water flowing through the gully, and a gully is larger than a rill, even if there's water flowing in a rill, etc. Okay, so I maybe gave a little bit too much away earlier in this lecture on this, but I'm still going to ask you to do this in-class activity. I'm going to take a minute and think about these questions. So I want you to think about if you've ever seen sheet flow occurring, and if so, where, and how often have you seen sheet flow occur? And then after you think about those questions, I want you to answer, do you think that sheet flow is responsible for most of the water flowing through the Boise River right now? And if you say yes to that, please explain. And if you say no, please explain. All right, so I would imagine that most of you have probably seen sheet flow. But again, I imagine you probably saw it most commonly flowing across concrete or pavement or some sort of man-made structure that has an extremely low hydraulic conductivity and doesn't allow water to flow through it. And that's just a testament to how man-made structures really alter the land surface and how that alters the hydrologic cycle. Outside of on top of concrete and pavement, etc., you may have seen it sometimes following a quick precipitation event or a long precipitation event or after snowmelt, most likely. But you probably haven't seen it super often outside of on top of those man-made structures like pavement or concrete unless you do a lot of hiking or outdoor recreation. And do you think that sheet flow is responsible for most of the water flowing in the Boise River? Well, there hasn't been a super recent precipitation event. So right now, the majority of the water flowing in the Boise River is most likely fed by groundwater. Now, if you have a flooding event in the Boise River following a precipitation event, then sheet flow might be responsible for most of the flow in the Boise River, especially, again, if it was a very rapid precipitation event or snowmelt event, or a very long precipitation event or snowmelt event. Because, again, those are the two ways that cause most of the water to run off as sheet flow rather than infiltrate into the soil. So we've talked a little bit about how vegetation canopy and evaporation of water from the canopy after it fell as precipitation and transpiration impact what happens when precipitation falls and snow melts. But we haven't talked about how transpiration, or again, when plants take water up from the soil into their roots and then transpire it through the stomata or the pores in their leaves, we haven't talked about how that affects stream flow. So a good case study for this is, again, looking at this local stream, Dry Creek, that runs near Bogus Basin. And the figure that I have here on the right side of your screen is what's called a hydrograph. And this is the same type of graph that you can look at if you want to look up the stream flow of a number of streams and rivers in the United States through the U.S. Geological Survey. And you can just look up that information online. So this graph basically shows discharge on the y-axis and then time on the x-axis. And you can see that I have a subset in the upper right where I zoomed into the summer months of the hydrograph of Dry Creek here. And you can see that every day you have a fluctuation up and down in stream flow. And this isn't because it rained every day, because it hardly ever rains in the summer in Boise. So a lot of what this is actually from is groundwater that would have made its way to the stream and contributed to stream flow being intercepted by plants that transpire that water during the day and then don't transpire that water at night. So typically you have greater stream flow at night than you do during the day when there hasn't been any recent precipitation in Dry Creek. And you'll see this in other streams and rivers as well. The only complicating factor is that sometimes there's a lag time or a number of hours or days in between when plants next to the stream are transpiring water and then when you see the lowest stream flow as a result of that. It depends on how long it's taking for the groundwater to travel from the hill slopes to the stream. Okay, so we've talked about kind of the global hydrologic cycle, and then we've zoomed into a hill slope scale and talked about that. But what we haven't talked about are drainage basins or catchments and the hydrologic cycle on that scale. So larger than a hill slope, but smaller than the global scale. So drainage basins are basically areas of land that are drained by a single stream. So that stream that I just showed you a hydrograph of, Dry Creek, it's surrounded by Dry Creek Experimental Watershed, or Dry Creek Drainage Basin. Watershed, catchment, and basin, they all mean the same thing. And the way that that drainage basin is delineated is by determining where on the land surface water would fall and then ultimately find its way to that stream if the water were to run off across the land surface. So the line that you would draw to delineate the Dry Creek drainage basin, for example, is an imaginary line that separates the Dry Creek drainage basin from an adjacent drainage basin, and this is called a divide. A lot of times the divides are visible as high ridges in a mountainous region, but they can be a little bit harder to determine if you don't have a lot of topography, or if topography is subdued, in which case you might need like a digital elevation map to determine something like that. And a larger divide called a continental divide, which you may have seen signs for if you've ever driven east or west on some of the interstates around here. A continental divide splits a continent into different drainage basins. So anytime you cross a continental divide, all of the water that would fall as precipitation or snow and then later snow melt on one side of the divide would flow in one direction, and on the other side of the divide it would flow in another direction, for example. So let's talk about drainage basins and divides, again using the Dry Creek Drainage Basin, or also shown here is the Dry Creek Experimental Watershed as an example. So in the figure on the right, you can see the drainage divide and how on either side of the divide you can see rills and gullies, but it appears as though water would flow in opposite directions on either side of the divide. So again, that's how you delineate a drainage basin slash catchment slash watershed. So if you look at the figure on the left, or Dry Creek Experimental Watershed here, this has basically been delineated by looking at the red dot that's labeled with an LG in the bottom left here, and then determining what areas would runoff ultimately flow towards that point on Dry Creek. And so that is how the drainage divides were drawn that would funnel water to that location on Dry Creek. So the reason why we care about delineating drainage divides into catchments slash watersheds slash drainage basins is because it gives us a much better understanding of the water balance, or how much water is available for humans and for local ecosystems. And it also helps us to make better water laws and determine what sort of water rights should be made available to people that still allow for a sustainable hydrologic system. So you can basically use a mass balance equation to infer the magnitude of hydrologic fluxes within a drainage basin. So an equation, a mass balance equation that you would use is inflows to the drainage basin minus outflows from the drainage basin equal the change in storage in water in that drainage basin. And this mass balance calculation that you can make within a drainage basin makes these basins useful sort of laboratories for a number of hydrological processes. And so these drainage basins can be used to attain a better understanding of each arrow or each flux within the hydrologic cycle. So, for example, to calculate the mass balance within a drainage basin, we need to know what are the inflows to that basin? Where's water coming from? What are the outflows from that basin? So how does water escape the basin once it's already in there? What are the storage reservoirs, or where is water held within the basin? And how much does storage of water change over time? And then lastly, we can think about what sorts of hazards predictions are improved with a better understanding of the hydrologic fluxes, or the way that water moves, and the water balance, or how much water is in a drainage basin. So looking at this mass balance equation to figure out how much water is available for any purpose within a drainage basin, what are the inflows to a basin? Well, typically the only major inflow is precipitation. It could be in the form of liquid water or snow. And groundwater is an unlikely or minimal inflow to a drainage basin. And I want you to take a minute to try to figure out why before I tell you. So groundwater is an unlikely or minimal inflow to a drainage basin because of the way that drainage basins are delineated. So usually the water table, or the height of groundwater, is sort of a subdued replica of topography. And so if you're delineating a drainage basin where the highest elevation points around a stream make the edge of the drainage basin, then it's sort of unlikely that groundwater would come from the other side of your drainage divide and then come into that drainage basin. Similarly, it's unlikely that groundwater would flow from inside your drainage basin outside of your drainage basin unless it was at the bottom of the basin near the stream. What are the outflows from a drainage basin? Well, you have runoff, so in the form of stream flow. You have deep recharge, and this is when groundwater infiltrates deep within the earth without resurfacing or entering into the stream. And usually this is a certain percentage of overall precipitation that participates in deep recharge. And then you have evaporation and transpiration are also outflows, because a certain percentage of precipitation is evaporated or transpired back to the atmosphere before it would ever leave the basin as runoff, for example, or as deep recharge. What are the storage reservoirs that you should be aware of? So one is the snowpack, as we talked about before. It's storing water on the land surface. Another one is surface water. So even if water is in a stream or a river, that's still a storage reservoir or a place where water is held. And a third is soil water. So when I say soil water, I generally here mean the unsaturated zone of soil. And then the fourth storage reservoir is groundwater, which is the saturated zone of soil or rock where all of the pore space is filled with water. And it's important to know how much storage of water changes within a drainage basin. And this really depends on the time scale that you're talking about. So seasonal changes in storage of water can be large. For example, if you think about the Dry Creek drainage basin, it's probably going to store a lot more water in the winter than it does during the summer, because the winters see a lot more precipitation in that area than the summer does. And there's a lot of water storage as snowpack at that time. However, despite that fact, annual changes within a drainage basin, annual changes in storage, are often assumed to be zero. And I want you to take a minute and think about why that might be, and then we'll discuss. Okay, so annual changes are often assumed to be zero because, first of all, that makes the mass balance equation at the top of this slide a lot easier, because all you have is that the runoff is equal to the inflow minus the outflow, basically. And secondly, it's because if you're talking about annual changes in storage of water, then you're talking about the same day of the year. So you might say October 1st of one year till October 1st of the next would be one water year. And annual changes therefore would be much less pronounced because you don't have the larger seasonal changes involved. All right, so I have an in-class activity for you, and I would like you guys to try to use this mass balance equation to calculate some information about Dry Creek. So let's say that you have a job as a hydrologist, and your boss asks you to calculate the amount of evapotranspiration in Dry Creek Experimental Watershed for the 2020 water year. And he gives you the following information. You have the equation that inflow minus outflow equals change in storage. You can assume that the change in storage is 0 because we're doing this analysis for an entire year, and that removes any seasonal variability in the change in storage. The average precipitation throughout the entire watershed is 20 millimeters of precipitation. And your stream flow at the catchment outlet, so at that red dot marked LG, is 12 millimeters of stream flow if you were to distribute it over the land surface and across the entire water year. And then deep recharge, or water that fell as precipitation that infiltrated into the deep groundwater and then left this catchment, has been found to be approximately 20% of the annual average precipitation in the basin. So I'm going to give you a few minutes to try to calculate what the evapotranspiration is for the 2020 water year. Remember that you need to decide what numbers that I've given you here are inflows to the system and what numbers are outflows to the system to make this sort of calculation. Okay, so let's walk through this. So you know that your change in storage is 0. So you have basically inflows minus outflows equal 0. And so let's determine which numbers that I gave you are inflows and which ones are outflows. So you have an average precipitation in the basin of 20 millimeters. That's an inflow to the basin. So it's where did the water come from? It came from precipitation. Then you have stream flow at the catchment outlet. That is 12 millimeters. And again, that's sort of, if you were to take the entire year of water flowing out of there and then distribute it over the area of the catchment, you get 12 millimeters. So since that water is leaving the catchment as runoff, that is an outflow. So right now you have 20 millimeters minus 12 millimeters as inflow minus outflow. And then you have deep recharge has been found to be approximately 20% of annual precipitation. Well, annual precipitation is 20 millimeters, and 20% of that is 4 millimeters. And we know that deep recharge is an outflow because this is how groundwater leaves the catchment or leaves the drainage basin. So you have 20 millimeters minus 12 millimeters minus 4 millimeters. So right now you have basically, you have 20 minus 12 minus 4. That leaves you 4 millimeters. And your equation would say, inflow minus outflow is 4 millimeters equals a change in storage of 0. Well, what you're missing is the evapotranspiration, which is the other outflow from the catchment. And we know that 4 doesn't equal 0. It in fact equals 4. So if you were to assume that the evapotranspiration that year equaled 4 millimeters, then you could say, okay, you have a precipitation of 20 millimeters minus 12 millimeters of stream flow minus 4 millimeters of deep recharge minus 4 millimeters of evapotranspiration. And then you've balanced your mass balance equation, and therefore your evapotranspiration must have equaled 4 millimeters. If you have any questions about how to make this type of calculation, I really wish that I could have went over this with you in class on a whiteboard, so please reach out. So let's talk about different types of drainage patterns that can form when rills combine to become gullies, and gullies combine to become streams, and streams combine to become rivers. You have a dendritic pattern, which is the upper left, and this develops on relatively uniform surface materials, or if the geology of the area is relatively consistent. And then in the upper right, you have a rectangular pattern, which develops on a highly jointed bedrock. So if you have a solid rock that's been fractured in a very specific way, or fractured in a jointed sort of way, then that can lead to this rectangular pattern. You can have a radial pattern, which is in the lower left, and that develops on sort of isolated volcanic cones or domes. And then you have a trellis pattern in the bottom right, which develops in areas of alternating weak and resistant bedrock. So in the areas of weak bedrock, streams will form deeper valleys, and then in the areas of harder bedrock, not as many streams will flow through there. Only the main stream will flow through there, or the largest stream. So out of these 4 drainage patterns, what type of drainage pattern would you say that Dry Creek Experimental Watershed exhibits? I'll give you a moment to think about that. Okay, so it actually exhibits a dendritic pattern. So if you go back and look at the slide, the shape of all of the tributaries flowing into Dry Creek and how Dry Creek flows out of the basin looks a lot like the dendritic pattern shown on the upper left on this slide. And it makes sense that it would show a dendritic pattern because the geology of that watershed is relatively consistent. The bedrock's primarily made of granodiorite, and it has a shallow layer of soil on top of it. So let's talk a little bit more about river systems and move beyond just drainage patterns to river systems as a whole. So rivers drain much of the land area. Exceptions are extremely arid or polar regions. So if you're in the middle of the Sahara Desert, you're probably not going to find a river draining much water. Or if you're in Antarctica and it's the winter, you're probably not going to find a river draining much water. But everywhere else, you're likely to find them. And it's important to note that everywhere else where you will find rivers, that climate differences and human intervention influence the character of a river. So one really good example of this is a project that I'm working on at Idaho Department of Water Resources. So I do a lot of work on the Lemhi River and the Upper Salmon River, where agricultural processes have modified stream flow and modified sediment delivery to streams and modified the riparian zone, or the area of vegetation on the stream or river banks, and that has influenced the character of those rivers over time and made them less hospitable to Chinook salmon and sockeye salmon and steelhead, for example. So I'm working with some folks to try to improve the salmon habitat in those areas. Differences in climate also influence the character of a river, because obviously if you have changes to climate, then you're changing your inflows and outflows from drainage basins that feed rivers. And therefore, you're going to have different stream flow and sediment transport and ecological systems develop as a result of those changes. So regardless of what sort of climate regime you're looking at or how much human intervention you've had, you can divide river systems into essentially 3 zones, which are a zone of sediment production, a zone of sediment transportation, and a zone of sediment deposition. And we'll talk about those in a little bit more detail now. So the river system's zone of sediment production is the zone where the most sediment is derived, so where the most sediment is eroded from. And this is typically located in the headwater region of a river system, the headwater being the most upstream regions of a river system. And so often the steepest section of the river system where the water that's moving sediment has the most energy to move sediment and to erode it away. In these areas, sediment is generated by bedrock that's broken into smaller pieces, erosion of the stream or river banks, and then scouring of the channel of the stream or river as well. The zone of sediment transport is basically where streams are below the headwater area and above, significantly above the lake or ocean area where sediment is ultimately deposited. So in the zone of sediment transport, everything is basically in balance, meaning that the amount of sediment being eroded by the stream or river is roughly equal to the amount of sediment being deposited by the stream or river. So you can think of these as kind of an intermediate or like an average like grade. It's not some river that's like roaring down a steep mountain, but it's also not extremely flat like the Mississippi River before it dumps into the Gulf of Mexico, for example. And then there's the zone of sediment deposition, which is when a river reaches a large body of water like a lake or an ocean, the energy of the water that's carrying that sediment decreases, and therefore the river deposits those sediments because the energy is not great enough to keep the sediment entrained or suspended within the water. And typically only fine sediments are deposited in the oceans, because most of the time something that's a sand size or larger will be deposited before it makes it far out into an ocean basin. That's why a lot of times when you go to the coast, you'll see a sandy beach, for example, is because all of the sand fell out of suspension and got deposited as soon as the river water hit the ocean, because the ocean didn't have enough energy to carry that sand far out into the ocean basin. So this figure shows a really good example of these 3 zones of a river. The headwaters being the zone of sediment production or erosion, so sort of the steep mountainous areas, and then the zone of transportation, basically being the intermediate area below the like steep slope mountain areas, and the area where the river flows into a lake or an ocean. And then the zone of deposition is near or at where the river flows into a lake or ocean, and the vast majority of the sediment falls out of suspension. All right, so we've talked about runoff and we've talked about the water balance. But how do we know how much water is actually running off in the form of a stream or a river and leaving a drainage basin? Well, the term discharge is the term that we use to refer to the volume of water flowing past a certain point in a given unit of time. So if you think back to the example of the mass balance equation or the water balance that we did in Dry Creek Experimental Watershed, where we looked at that red dot LG, which is a stream gauge on Dry Creek, essentially what you're doing is you're measuring the discharge or the volume of water flowing past that point or that gauge in a given unit time. And one really great place to find this sort of information, as I've spoken about a little bit earlier in this presentation, is from the U.S. Geological Survey, who I used to work for in New Mexico. And they have sites all across the country where they measure the flow velocity, discharge, and the river stage, or the height of the water surface of the river, at fixed points. And you can just look up this information online and then use it for whatever you need, to determine whether an area is likely to flood, to determine if there's enough water flowing by that you can divert water, to determine what the conditions might be like for fishing, etc. Anything you need, the information is made readily available to the public. So now I'm going to show you an example of this data set. All right, so this is an example of a USGS hydrograph of the Boise River at Glenwood Bridge near Boise, Idaho. And again, on the y-axis you have discharge in cubic feet per second, and on the x-axis you have time. So I basically downloaded data for January 1st, 2020 through November 1st, 2020. And you can choose your time frame when you're selecting data from the USGS website or from the Idaho Department of Water Resources website for that matter. And then on the y-axis you can see that this is a logarithmic axis. So on the bottom you have 100 cubic feet per second, on the top you have 2,000 cubic feet per second, and every line on this chart represents an extra 100. So you can see that the Boise River generally varies between about 200 and 1,000 cubic feet per second within the past year, and that you have much higher flow in the spring and summer than you do during the winter. And I guess I'll give you a second to think about why that might be, and then we'll talk about it. All right, so there are really two factors at play here. The first thing to note is that the Boise River is actually controlled flow, because the water in the Boise River flowing past Glenwood Bridge, the majority of it is actually released from Lucky Peak Reservoir, so the amount of flow is controlled. But nevertheless, the discharge in the spring and summer is higher than during the winter, because they have to let additional water flow out of Lucky Peak Reservoir in the spring and summer due to the timing of snowmelt, which is the largest contributor of water to the Boise River for much of the year. So whenever I'm showing you these hydrographs of, for example, Dry Creek or the Boise River, and I'm talking about the discharge in those creeks and rivers, it's kind of important to understand how the discharge is calculated, because it's not exactly a direct process, right? We don't have the technology to directly determine exactly how much water is flowing past the point at any given time, let alone throughout an entire year. So we have to use known relationships to get a best estimate for the discharge. So typically what's done is something called a rating curve is formed, and a rating curve is basically a graph and an accompanying equation that represents the relationship between the stage, or the height in feet above a datum within the stream that the stream water is sitting at, and the discharge in cubic feet per second that that river or stream is flowing at when the stage is at that elevation. So in the bottom right here, you can see a good example of a rating curve. So on the Laramie River near Fort Laramie, Wyoming, you can see that when the stage is about 6 feet above their datum, that the discharge is about 2,000 cubic feet per second. And when it's about 8 feet above their datum, that the discharge is about 5,000 cubic feet per second. So essentially, researchers or data scientists have to go out into the field and make measurements of what the discharge is when the stage is at different heights, and then you leave something at the stream location to record the stage, or the height of the stream or river continuously, and then you use your knowledge of that stage to compute what the discharge is when you're not there to actually measure discharge yourself. When you're on site as a hydrologist or a technician and you're measuring stream flow yourself, there are a number of different methods that you can use to do this, ranging from an acoustic Doppler velocimeter, which basically detects how fast particles of water move from one location on your instrument to another, to an acoustic Doppler current profiler that actually tracks how fast particles are moving from one location to another throughout the entire depth of the stream, to something called dilution gauging, which is monitoring the appearance of a tracer like a salt or something that you put in the stream at a downstream location and calculating how long it takes to get there. But you're essentially calculating the discharge in one of those three ways. So let's talk about how a stream channel changes from its head to its mouth. So, we've talked about how sediment transport varies from the headwaters to the mouth of a stream, but several other changes also take place as the stream travels from its origins to where it delivers its water to a lake or an ocean, for example. So this graph shows a number of different stream-related attributes and how they change as you move from the headwaters to the mouth. So as you can see, usually the flow velocity increases, even though the channel slope, or the gradient, decreases as you move towards the mouth. But the reasons why the flow velocity would typically increase is that, for one, the channel roughness decreases typically as you go from the headwaters to the mouth. And for two, the total discharge typically increases as you go from the headwaters to the mouth, because you have more inflows adding to that stream flow as you continue to move downstream. Could be gains from groundwater, additional gains from precipitation, etc. And then the channel size also usually increases as you move downstream. For example, you would never see something that looks like the Missouri River or the Mississippi River up in the mountains, because the greater discharge and the greater total amount of water that you see further downstream towards the mouth makes the channel size larger as well. So let's talk a little bit more about the work that running water performs and how that leads to erosion. and how those erosional features can tell you something about the history of the river that you're looking at, and also inform you on some safety concerns. So the erosion caused by a stream is related to the slope or the gradient of the stream, the discharge, or how much water is flowing past a point at a given time, and the nature of the stream bed and the stream bank sediments. So for example, sand-sized particles are easily eroded, whereas silt and clay-sized particles and gravels are often harder to erode. So channels with, sort of cohesive silty bottoms are typically more narrow than sandy channels because sand-sized particles are more easily eroded. And so it makes for a wider channel because it takes less work to erode those particles away. So there doesn't have to be as much water flowing over them, flowing over sand particles to move them. The term quarrying involves removing large blocks from the channel bed during flood events. So during flood events, you can move much larger pieces of sediment and rock because of the increased energy of the water and therefore the increased amount of work that it's capable of doing. And by scraping, bumping, and rubbing, abrasion both erodes sediments and polishes them. So abrasion is basically when you have sediment that is being moved downstream that's scraping, bumping, and rubbing against other sediments or rocks, and eroding them and also polishing them. Potholes form when fast-moving, swirling sediment in eddies abrades a hole. So if you're ever hiking along a river and you look at a rock and you see something that looks like a pothole, it's probably from when flood events swirled sediment around in eddies and abraded those potholes. And then finally, you have stream erosion in the form of corrosion, which is when rocks are gradually dissolved in the flowing water. And this commonly occurs in limestone bedrock channels because limestone, which is made primarily of calcium carbonate, can be easily dissolved by slightly acidic water, as you might have noticed in lab when you put hydrochloric acid on limestone, which is a little bit more acidic than water, but you get the idea. So this just shows some really good examples of potholes, in this case in some sandstone canyons. So we've talked a lot about how different types of streams erode sediment in different ways, and different sections of streams, for example, the headwaters and the transport area and the deposition area, might erode sediment or transport sediment or deposit sediment on average. But it's important to talk about what exact types of mechanisms are moving this sediment within the streams. So all types of streams and all sections of streams do transport sediment. It's just that some areas within streams deposit more sediment than they transport or erode. And there are three primary types of sediment transport that you should know about. The first one is called dissolved load. So this is basically particles dissolved in solution. And you can't see this with your naked eye. It's kind of like taking sugar or salt and putting it in water and then stirring it with a spoon. The sugar or salt gets dissolved in solution and you can no longer see it. The second type is called suspended load, and this is when sediment is caught in suspension or within the water column in the stream. And this typically happens with particles such as silt or clay, and that's just because the stream has enough energy, or the movement of the water
has enough energy to keep those particles in suspension. Sometimes in very fast-moving streams, you can have something like sand or gravel as part of the suspended load, but those are typically more so flood events and really massive discharge streams. And then the last type of sediment transport is bed load. And bed load is basically all of the particles that are sort of rolling along the bottom of the stream. So they might, those particles might exhibit saltation, which is kind of like bouncing. They might be sliding across the bottom of the stream, or they might be rolling. But no matter how they're moving, as long as they're sort of moving across the bottom of the stream, that's called the bed load. So most of the dissolved load is brought to the stream via groundwater. So as we've discussed before, a lot of stream flow is actually derived by groundwater that seeps into the stream banks and contributes to stream flow. And so a lot of that dissolved load is from groundwater. If you take a second to think about why that might be, well, it's largely because water is in contact with rocks and sediment below the ground for a really long period of time, right? Groundwater doesn't move nearly as fast as surface water does, typically. So it gives that water a lot more time to dissolve part of the rocks and sediment that it's coming into contact with below the ground, and therefore the dissolved load in groundwater is usually much greater than it is in stream water that's not derived primarily from groundwater. It's important to note as well that the dissolved load is not affected by the stream velocity or the velocity of the stream flow. It's basically just related to the chemistry of the water and whether or not the conditions are good for the water dissolving minerals, or in contrast, if the conditions are good for the water precipitating minerals. So dissolved minerals precipitate from the stream water when water chemistry changes. So you can think of this, for example, as, let's go back to the putting salt into a cup of water example. If you put salt into a cup of water and stir it with a spoon, then it will dissolve and get to the point where you can no longer see the salt and then be part of the dissolved load in that glass of water. However, if you continue to put more and more salt in there, eventually it will reach a point where the energy or the movement of that water is not enough to hold all of that salt in suspension anymore. And then some of that salt will begin to precipitate out into salt crystals. So let's move on to suspended load. This is actually the largest part of the stream load, or you might think of it as the transport mechanism that transports the greatest amount of sediment within stream flow. And the amount of sediment or material that's carried in suspension in a stream is controlled by the velocity of the stream water and the settling velocity of the sediments. So the settling velocity is the speed at which a particle falls through a still liquid. In this case, it would fall through that still liquid to the stream bed. So let's think about this for a second. If the velocity of the stream is pretty slow, then it can probably only carry very small particles in the suspended load, like let's say clay-sized particles, because it doesn't have enough energy to hold those particles in suspension anymore. However, if the stream flow is very fast, then it's possible that a stream could hold, as I mentioned previously, something bigger like a sand or even a gravel in suspension. Gravel would be a very extreme case of very, very fast stream flow, but you know, maybe a lahar, for example, would be an example of that as suspended load. So this river is a really good example of a river that has a lot of suspended load. Anytime that you look at a river and it just looks muddy or it looks pretty brown, then it has a very high amount of suspended load. And you might not see this in the Boise River so much in the Boise area, but you see it in a lot of other rivers that erode a lot more silt and clay and hold that in suspension. It's for example very, very common on the East Coast where I grew up. You know, we have a lot of sediment and a lot of sedimentary rocks that are being eroded into the streams, and then a lot of that sediment stays suspended within those streams, like the Allegheny River or the Ohio River, for example. And then finally, onto bed load. So again, this is usually like coarse sands, gravel, and boulders moving along the stream bed. And it's generally a less rapid movement than suspended load or dissolved load. And this is, you know, because these particles are larger, for one, and also because they're sort of hitting off the bottom of the stream bed, and that friction slows down the movement of those particles. And the movement is usually more localized as well, meaning that just because you have a substantial bed load in one area doesn't mean that you'll also have a substantial bed load in another area in the stream. It just really depends on the velocity of the water at your given location. And so this photograph shows a really good example of bed load. You know, a lot of these gravel-sized particles that you see were sort of moved across the bottom of this stream when the water was flowing more rapidly. So there are a couple more terms related to transport of sediment within streams that will help you conceptualize this process. The first term is called capacity. So the capacity of a stream is the maximum load of solid particles a stream can carry. So the greater the discharge of the stream, the greater the capacity. So you can think of this as, you know, if you have an extremely small stream that's flowing very fast, well, even though it's flowing very fast, it can only carry a small load of solid particles with it because it's a small stream. There's not a large body of water that's moving that fast to carry particles with it. But if you have a very large river that is flowing at the same velocity as the smaller stream that I just described, then the capacity of that very large river is much larger, because not only can it move those larger particles, but it can also move a lot more of them because it's a much bigger body of water moving down slope. The second term is competence, and this is the term that I've sort of been referring to when I talk about the energy of stream flow being able to carry particles or not. So the competence is the maximum particle size a stream can transport. And streams with a faster velocity have a higher competence. So let's go back to the example that I just used for capacity. And we'll take that. We have the small stream that's flowing very fast, and then we have a large river that's flowing at the same speed. Well, both of those, both the small stream and the large river would have the exact same competence, because they can both move the same maximum particle size because whether or not a stream or river can move a particle size is dependent upon the velocity. Okay, so moving on from erosion of sediment to transport of sediment to now deposition of sediment in more detail. So deposition of sediment occurs when a stream's flow velocity is less than the settling velocity. If you recall, the settling velocity is the velocity of stream flow at which particles will fall out of suspension and settle on the stream bed. When particles are deposited, particles of the same size are deposited at the same time in a process called sorting. So in this case, larger particles settle out first. So let's think about a stream having a flood event, right? You've got some spring snow melt, and the discharge of that stream is way higher than normal. But the flood event only lasts for a day. Well, at first, that stream is going to be carrying very large particles in its suspended load as well as in its bed load. However, as stream flow slows down, as the snowmelt event stalls, let's say the temperature goes back below 32 degrees Fahrenheit, then the stream flow velocity will begin to slow down. And so you already had some of the large particles settle out. Now some of the smaller particles start to settle out because the velocity is slowed down. And then that process will continue. So you have the large particles settle out first, then the medium-sized particles, then the small-sized particles, all because the velocity of stream flow was slowing. And again, this is called sorting. And sediments deposited by streams are generally referred to as alluvium. This is going to be important for you to remember if you move on as a geology major or if you ever look at a geologic map for any reason. So a lot of times when you're looking at a geologic map, right next to or adjacent to a stream, you'll see something marked as alluvium, and that just means sediment that was deposited by streams. So although a lot of stream channels may have sand or gravel or cobbles on the stream bed, there is another type of stream channel that you should be aware of called a bedrock channel. And these channels are cut into the underlying strata or into the underlying bedrock. They typically form in the headwater region, so at the highest elevations of the stream or river, and have a steep slope. And potholes and features that look like stair steps and pools are common features in bedrock channels. And in this case, the channel pattern is controlled largely by the underlying geology rather than how particles are deposited influencing the channel pattern. So the stream or river would generally cut down through the bedrock in areas of weakness or fracture, and that would determine the shape of the stream channel. Alluvial channels, as I just alluded to or alluvialed to on the last slide, form in sediment previously deposited in the valley. So this photo on this slide shows a good example of that. So maybe in larger flow events, you had a bunch of sediment that was eroded upstream, transported to this location, and then deposited as the flood event subsided. And then the stream channel cuts through the floodplain that has been built by the deposition of sediment in this area previously. And these types of stream channels change shape a lot more often than something like a bedrock channel, because it's very easy for the stream or river to simply cut through the floodplain or the deposited sediment if you have an event with higher stream flow. And as a result of how easy it is to cut new paths through the deposited sediment in alluvial channels often form meandering or braided shapes of stream channels. So speaking of meandering channels, in the case of this type of channel, streams transport suspended sediment in broad sweeping bends called meanders. And meandering channels evolve in shape over time. These terms, cut bank and point bar, that I'm about to talk about, they really exist in the vast majority of streams and rivers that you're going to look at. So even though not all streams and rivers are alluvial channels and meandering channels, the majority of them that you will observe actually are, especially if you're kind of down in a stream valley rather than up in the mountains near the headwaters. So the reason why meandering channels evolve over time is because the outside of a meander, which is known as the cut bank, is a zone of active erosion, and the inside of a meander, known as a point bar, is a zone of deposition. And through time, the bends in the channel, or the meanders, migrate as a result of this erosion and deposition, and they can eventually even join together. So a meander that has been cut off from joined bends or meanders is called a cut-off oxbow lake. So a lot of times a lake is left behind in the meander or bend in the river that got cut off from current stream flow patterns because the two bends or meanders joined together. So if you imagine a bend in a stream and you have your cut bank, which is on the outside of the bend in the stream or the meander, eroding sediment. Let's say that's on the right side of the stream when you're looking upstream. And then you have a point bar that exists on the inside of the meander or bend in the stream in a zone of deposition. If you're looking upstream and that point bar is on the left and the cut bank is on the right, I want you to think about which direction you think the meander would migrate over time. And think about that for a second, and then I'll discuss. So if you have the outside of the meander or the cut bank being on the right, and the inside of the meander or the point bar being on the left, and the cut bank is eroding sediment away, then the meander would typically move further to the right over time because it's eroding sediment on the right side of the stream and depositing sediment on the left side of the stream, thereby migrating the channel in the direction of the cut bank over time. So this diagram shows a couple things. It shows real-life examples of meanders, cut banks, and point bars in White River near Vernal, Utah on the left. And it explains why sediment is being eroded on the outside of the meander and being deposited on the inside of the meander. So the reason is If you imagine all the water is flowing in the same direction, and then it goes into a curve, then on the outside of the meander, for that water to keep up with the water on the inside of the meander, it has to move faster. And because it's moving faster, it's more likely to erode sediment. Versus the water on the inside of the meander doesn't have to move as fast to get around that curve because it has a lesser distance that it has to travel. And so it moves slower and therefore ends up depositing sediment on the point bar. The reason why the water on the outside of the stream and the water on the water on the outside of the stream meander and the water on the inside of the stream meander don't just vary drastically in the speed at which they're moving is because water is a liquid, and so therefore there's sort of the force of momentum and drag where the water on the outside of the stream isn't moving entirely independently from the water on the inside of the stream meander. And then this slide shows a really good example of the formation of an oxbow lake. So you can see very clearly that this is it's an alluvial stream bed. It's a meandering stream. And you had this big meander on the bottom of the photo of Green River in Wyoming. And then it looks like, you know, two of the meanders connected with one another. And then ultimately the Green River just ended up flowing straight through that area as a result of that. And so it cuts off an oxbow lake that remains there as a lake, but is no longer part of Green River because it's no longer flowing. So another type of alluvial channel that we've talked about is a braided channel. And this is different from a meandering channel because it's a network of converging and diverging channels that thread among numerous islands or gravel bars. And in the case of a braided channel, a large portion of the load, including bed load and suspended load, is coarse material. And this is different from a meandering channel in which typically the load was primarily composed of silt, clay, and perhaps sand. In a braided channel, usually the discharge of the stream or river is highly variable, and this oftentimes is a result of seasonal variability. So, for example, in some climates like ours here in the Boise and Nampa area, we get a lot more precipitation in the winter than we do in the summer. And that seasonal variability, if you are in a high mountain area, can lead to the formation of a braided channel. And in a braided channel scenario where you have all these converging and diverging channels that thread among numerous islands or gravel bars, as you might imagine, the bank material is relatively easily eroded and reworked. So this photo right here is an example of a braided stream. So it's not necessarily what most people think of as the shape of a stream. Maybe most of you have seen less examples of this than you have of a bedrock channel or an alluvial channel that resulted in a meandering stream, for example. But they are still actually quite common. If you go to a glacier, for example, a lot of times the water that's draining from a glacier that forms a river results in a braided stream. And I've seen this a number of times in Iceland and Alaska in my travels that I've been fortunate enough to have. Okay, so we've talked about the different types of stream channels and how those different types of stream channels shape stream valleys differently based on the nature of erosion and deposition and transportation of particulate matter or sediment. Let's talk about a couple more ways that stream valleys are shaped. So there are a couple vocabulary terms here that you need to keep in mind to understand this discussion. The first one is base level. And the base level is the lowest elevation to which a stream can erode its channel. And the base level can really be broken down into the local base level and the ultimate base level. The local base level is a lake or resistant layers of rock in the case of tributaries. And the ultimate base level is sea level. The local base level is called that because it is the lowest elevation to which a stream can erode its channel locally, versus sea level is the ultimate base level because a stream is not going to erode its channel to below sea level if it flows into the sea, which makes sense, right? Because water flows downhill. So a stream can't flow below sea level if it flows into the sea, and a stream can't flow below a lake if it flows into a lake. So if you take the base level and you raise it or lower it, then it removes the stream from a state of equilibrium. A state of equilibrium meaning that you're not changing the lowest level to which the stream can erode its channel over time. That's just remaining constant. And so if you were to take the base level and raise it, so let's say that a lake gets deeper, or sea level, a lake, the maximum height of water in a lake gets higher, or sea level gets higher. That can cause deposition. However, alternatively, if you were to lower sea level or lower the lake, then that can cause erosion. And I'm going to give you a second to think about why raising or lowering the base level would cause deposition or erosion, and then I will discuss. Okay, so if you lower the base level, then you've lowered the level to which a stream can erode its channel. And if you do that, then the stream will naturally erode its channel lower. And if it's eroding its channel lower, then that causes erosion. However, if you raise the base level, then you've effectively changed the gradient of the stream to a lower gradient, because if you think about the feet per mile that the stream is dropping from its headwaters to the lake that it's flowing into, or the sea that it's flowing into, well, if you raise the elevation of the endpoint that it's flowing into, or its base level, then you've decreased the gradient, and therefore water would flow slower, and therefore you would have more deposition, especially at the base level itself. So at the lake or the sea, you're going to have additional deposition of sediment at that location, but also overall, because you've changed the gradient. So let's talk about how building a dam would change the base level and what impact that would have on erosion and deposition of sediment. So in the upper portion of this figure, you can see the profile of a stream that is adjusted to base level, and it's in equilibrium. In this case, it's flowing into the sea, so it's at the ultimate base level. And then instead, humans decide to build a dam. Well, what does this do other than give us, water storage, flood control, and potentially electricity, and alter the ecosystem in a pretty catastrophic way for some of the wildlife that uses the river? Maybe that's the discussion for another day. Well, what it does from a physical perspective is that you have established a new base level for all of the river that exists upstream of the dam. And so here you can see the original profile, and then you can see the new profile that gets filled in with a bunch of sediment. And because you've given the river a new base level that's higher than the base level that used to exist there, so you've raised the base level, that's why you have the deposition of all the sediment. And in fact, at a lot of dams, including our dams here in Idaho, like Lucky Peak, for example, deposition of sediment behind the dams is a major problem. And if you have a dam in a location for long enough, a lot of times you need to come in and dredge that sediment and remove it, or else the reservoir will just fill up. Either that, or you need to just build the dam higher, and then you're adjusting the base level again, and then you'll have more deposition of sediment. So speaking of deposition of sediment, we've talked a lot about how erosion and transportation of sediment changes stream valleys, but we haven't talked a lot about the depositional landforms that occur as a result of the deposition of that sediment. So the major depositional landform that we need to talk about are deltas. So deltas form when sediment-filled streams enter a large body of water, like a lake or an ocean. When that happens, coarse sediments are deposited close to the river mouth. The mouth is where the river dumps into the lake or the ocean, while finer sediments are deposited at the outer edge of the delta. And this is because as soon as a large sediment like a gravel or a sand hits a lake or an ocean, usually the lake or ocean doesn't have enough energy to keep those particles in suspension, so they just fall out of suspension to the bottom of the lake or the ocean. And some of the finer sediments, because that river is feeding into the lake or the ocean, those finer sediments are still being carried by water that's moving fast enough to keep them in suspension, and so they get transported out to the outer edge of the delta. A really good example of this, and one of the more famous deltas in the world, is the Mississippi River Delta, which is actually a series of several coalescing deltas. And this is because over time, the mouth of the Mississippi River migrates, because you have all this deposition of sediment in the delta area, and then the river chooses a new path, because rivers like to choose a path where they're flowing at the highest gradient, or the easiest path for them to flow to the ocean or into a lake. In fact, right now, the Mississippi River is trying to cut through to the Atchafalaya River, and it wants to flow out the Atchafalaya River into the Gulf rather than flow in the path that is flowing right now. However, the problem with this, or at least as far as a lot of humans are concerned, the problem with this is that the Mississippi River flowing through the Atchafalaya River into the ocean would cause it to abandon its current course through New Orleans. And we've built up a lot of infrastructure in New Orleans as a port city, and a lot of people live there and rely on it being a port city, which makes it very inconvenient that the Mississippi River wants to flow in a different direction. So what do we do about this? Well, we don't move the city, because people are stubborn. what we do is we have engineering structures and dredging, so massive ships that go in and basically pull sediment out of the current Mississippi River to keep the gradient of the Mississippi River flowing where it is right now higher, so that it keeps the river from migrating down the Atchafalaya. It's pretty crazy. We spend many millions of dollars a year doing this. So this figure shows the growth of the Mississippi River Delta over time. So in the upper left, you can see areas of deltas that used to exist versus the area of the delta now. So number 1 is the oldest previous delta of the Mississippi River, which is, as a matter of fact, at the outlet of the Atchafalaya River. And then number 7 is the newest, so where the Mississippi River is flowing into the Gulf of Mexico now. And you can see that this forms a massive delta that's really a series of coalesced deltas that have been formed over time. So other than deltas, as far as depositional landforms, we have alluvial fans, and these are fan-shaped deposits of sediments at the base of mountain fronts. So maybe you don't have a stream or river flowing into an ocean forming a delta. Maybe you just have what's known as a ephemeral stream, which only flows part of the year, bringing sediment down from mountain fronts into a valley. And if you really look around the mountains just north of here or east of here or west of here, we're surrounded by mountains in this area. And you look at areas that look like they were drained by streams that aren't flowing, a lot of times you can see these alluvial fans around here. This photo on this slide is an example of an alluvial fan in Death Valley, which, you know, you're not going to see the stream channel flowing very often, but every once in a while when it rains there, it does transport a bunch of sediment from the mountain front down into the valley, depositing an alluvial fan. So that's all I have for you today. I didn't cover flooding very much in this lecture, so what I encourage you to focus on in your reading this week is the section on flooding in chapter 13, which is the end of the section. And the rest of the text, hopefully I've covered fairly well in this lecture. Next week we're going to talk about water a little bit more, and I'll get a little bit more detailed about some of the work that I do and have done related to water, so that not only do you have a good understanding of surface water and groundwater conceptually, but you also have an idea of the sorts of careers that you could pursue as a geoscientist or someone in another field working with water. You might notice the bullet point I have on this slide that says running water is life. Well, it's also the source of a lot of jobs, because it is, maybe the most essential resource for humans, as well as the rest of terrestrial life as well. So on that note, I hope you have a good week, and I will talk to you next week. Thanks. Bye.